podcast is brought to you by LMU Munich.
Well, this has been a marvelous conference, so let me join the other speakers and thank Dieter and the other organizers and everyone in a yellow shirt for making this such a nice and smooth conference, and also for being invited to present this work. So this is work in collaboration with John Estes, who is between Leuven and Imperial College. I'm not sure how to make this work. Where do I press?
Just press the big one, this one.
Oh, the big one. I'm sorry, thanks. Jaume Gomis from the Perimeter Institute and my student Benjamin Assel, who is here present. And actually the technical part of the talk is contained in these 3 articles. The third one, I was a little optimistic. It should appear in a week or 2, so it will be 1208. And really the technical part is some additions to ADS4CFT3, which is one of the holographic dualities that has both advanced very quickly in the last few years, and furthermore, which is particularly interesting, first of all, because we live in 4 dimensions, but also because little was known about CFT3 in 3 dimensions until a few years ago, and that's where holography, I think, has made a very big difference. So this is really what I will mostly explain to you technically. However, I want to actually explain a little bit the motivation that got me interested and started in this. And the motivation is a very simple physical statement, namely one of the most sacrosanct statements about gravity is that the graviton is massless and that it couples universally to all forms of matter and radiation. That's not true for any other interaction, right? We can have hidden sectors for gauge interactions, but nothing hides from gravity. Gravity is an absolutely universal force. Now, these properties are actually automatic in any compactification of string theory or any higher dimensional theory of gravity, and I will very briefly review the argument just to pinpoint the difference with the other interactions. And let me note that I will stick here with classical 2-derivative supergravities, so I'm not going to discuss stringy corrections or any other such effect. How does the argument go? The argument is simply Kaluza-Klein reduction for spin 2. So suppose you have any warped ADS space-time, namely this is some maximally symmetric, actually anti-de Sitter, de Sitter, or flat 4-dimensional space-time. This is some transverse space which may or may not be compact for the moment, and there is a warp factor which depends only on the transverse coordinates. Now, if you consider such a geometry and you try to reduce the spin 2 part, spin 2 in the 4-dimensional sense, the spin 2 excitations, what you should do is the following. Here is the consistent reduction of spin 2 metric perturbations. First of all, you only perturb the 4-dimensional part of the metric, and this 4-dimensional perturbation, which depends both on the space-time and the transverse or compact coordinates y, can be factorized consistently into a wave function psi that depends on the transverse coordinates and a spin 2 excitation, h mu nu, which actually satisfies, in general, the Pauli-Firth massive equations for a spin 2 particle, namely it is transverse, traceless, and it satisfies the the usual wave equation for spin 2 in a maximally symmetric space-time. So lambda here is the mass squared plus something that is 1, -1, or 0, 2, -2, or 0, according to whether you are in de Sitter, anti-de Sitter, or flat space-time. Now, if you just take this ansatz and you plug it into the linearized Einstein equations, for any sort of energy momentum tensor, which includes all other fields, p-form fields, scalars, and so on, you can actually show that this leads to a universal Schrödinger problem for the wave function psi in the transverse space. I insist here that this is universal, namely the equation only depends on geometry. It doesn't care about the matter fields or the p-form fields that came into determining this geometry. And there is a small argument which the experts know, but which you may have to rework out for yourself, which shows this for maximally symmetric four-dimensional compactifications. And the equation is the one I wrote here. So here is the mass operator for the spin 2. You see that it is essentially the covariant box in the transverse space, but with insertions of the warp factor e to the a in appropriate places. Okay, so that's a simple calculation. Now, if you use the standard norm that comes down from 10 dimensions for this wave function psi, it is given here, you can very easily show the following two things. First of all, the mass squared operator is non-negative. This is unitarity, that's automatic. But more importantly for us, you can easily show that the mass is 0 if and only if the wave function psi is constant in the transverse space. Okay. So what we can conclude with this very simple argument is that a massless four-dimensional graviton, first of all, requires that this norm be finite. This is automatic, of course, for smooth compactifications. But more importantly also that the couplings of this massless graviton are necessarily universal, because the couplings to any field phi are given by this integral. The effective couplings in 4 dimensions are given by this integral. Because psi 0 is constant, you pull it outside, the rest is the norm, and therefore everyone couples with the same strength. This is simply saying that you cannot have localization of gravity in any sense in this context. Can it be otherwise? Well, from this simple argument, we know that for this to happen, for something else to happen, we need at least two things. First of all, the graviton must be massive, it cannot be massless. Secondly, the transverse space must be non-compact. Okay. Well, a model for this has been proposed about 10 years ago by Karl Randall. This follows actually the earlier ideas of Randall-Sundrum and also Dvali, Papadadze, and Porati. But in a sense, the Karl-Randall setup is the controlled setup where you don't have to deal with various subtleties at the horizon and ambiguities at the horizon. And this is a model which may have a complete UV completion in string theory. So let me, in 3 or 4 minutes, describe to you what this does. Well, the model is very simple. It's 5-dimensional gravity with a negative cosmological constant. So you have basically ADS5 here, but then you add a thin brane with a tunable tension, little lambda, and then you solve the equations by using Israel matching condition, and the solution is of this very simple form. Y is the transverse coordinate. This is ADS4, so we are ADS4 foliating space-time, the ADS5. But then there is this warp factor here, which contains all the physics. The brane is situated at y equals to 0, so its radius of curvature is given by this particular combination of the parameters. It can be tuned, of course, to be infinite, so you can get arbitrarily close to an almost flat world. And this was, of course, part of the motivation in the Randall-Karp paper to relax the original condition of fine-tuning to 0 cosmological constant. Now, this is a very simple space-time. It is simply 2 slices of ADS5 glued along an ADS4 brane. Here is the picture. You take 2 global ADS5 space-times. You cut away these very thin green slices, which have a boundary that is ADS4, and then you just glue the 2 things together, and that's what we are describing. And the physics of this space-time is also extremely simple. It's enough to think about this warp factor as a function of the transverse dimension y, and to just describe the spectrum. Here is the spectrum of this thing. First of all, you see that out at infinity, we just have ADS5, so we have the usual infinite blue shifts of ADS5 boundaries. Then there are some minima of the warp factor, which are the centers of these cut-off slices that I showed to you, and which are the would-be horizons in the original Randall-Sundrum model, but here they are regularized by the fact that you have negative curvature. And then the brain is sitting here, and this warp factor, the scale of the brain, can go off to infinity, making it arbitrarily flat. Now, when you look at the spectrum, what happens is basically the following thing. There is one nearly constant, nearly massless mode. Nearly constant means that psi 0 is exactly constant here, and then it goes very quickly to 0 at the place where it is most favorable to minimize mass, namely at the bottoms of the wells. And there is a unique mode like this. And then there are the usual ADS5 modes developed as ADS4 representations, which are given by this spectrum. So that's a very simple model, you see. You have stuff down here, which is living down here, and you have an almost constant, but not exactly constant, psi 0 that lives in the middle of space-time. Well, these infinite towers of ADS5 modes are hidden sectors from gravity now, and gravity is not universal anymore, simply because psi 0 is not overlapping as before in a universal way with these localized wave functions. You can make this arbitrarily small. So that's a model for a massive graviton and hidden sectors. And hidden sectors is in a sense more crucial because the mass here is, the wavelength of the graviton is bigger than the radius of ADS4, so the mass doesn't have the usual sense of a screening length. Nevertheless, this is a model where there is no conventional effective four-dimensional theory, yet physics looks four-dimensional in a large range of parameters, namely between the ADS5 scale and the ADS4 scale. In particular, you get Newton's law with corrections that are given by this form. And as I said, here is a very simple model for how gravity can be non-universal. Okay. Now, warning, this is not a model for the universe. Lambda effective is negative, but I take the point of view that any long-distance modification of Einstein gravity is potentially interesting because it's the theory that we have so much trouble deforming, and therefore the problem should be taken very seriously. So the question is, can this thing be embedded in string theory? This is an obvious sanity check, in a sense, for any string theorist. And let me say that there is an obvious holographic dual question, because it is well known that this kind of brains are conformal domain walls in a four-dimensional conformal field theory. Here is the boundary of ADS5. There is a conformal field theory 4 living here, and this is the boundary of the brain, which is basically a domain wall. Well, there were two beautiful developments that got us started really on this question, and I will describe very briefly these two things. First of all, Docker, Estes, and Goodperl found the general local form of type 2b supergravity solutions with this much supersymmetry, that's half supersymmetry compared to ADS5. And at the same time, this is the symmetry of half BPS domain walls in N=4 super Young-Mills. And Gaiotto and Witten, in another very nice paper, proposed essentially a classification of these domain walls. So to address our question, basically we had to establish the precise dictionary between these two works. I will describe this now briefly. And as a bonus, actually, we will have some new lessons for ADS4 CFT3 that come out from this precise match. Let me describe very briefly the Gaiotto-Witten domain walls. These are walls which support a three-dimensional conformal field theory with N=4 supersymmetry. And this theory is the infrared fixed point of linear quiver gauge theories of the following type. So you have the usual gauge group factors. You have bifundamentals as usual connecting those. You have some fundamental hypermultiplets, M1, M2, and so on for the different gauge factors. And finally, you have the end points of the linear chain are connected to the bulk four-dimensional super Young-Mills through extra bifundamental hypermultiplets. Now, if we forget for a moment these extra couplings, this thing has a manifest global symmetry, which are the rotations of hypermultiplets, and the hidden global symmetry that you get from the mirror dual in the conformal fixed point. That's old stuff. Hanani and Witten have shown how to engineer these things by embedding them into brane constructions in type 2B theories. Mirror symmetry, so these are D3 branes suspended between NS5s with D5s giving the hypermultiplets. Mirror symmetry exchanges the NS5s with the D5s, and the best description of this type of theories is in terms of almost invariant linking numbers for the 5 branes. The 5 brane linking numbers are defined here. The linking number, say, for the D5s is the net number of D3s ending from the left on the D5s, so here it's 0 in this example, plus the number of NS5s to the right of the D5 in question. And there's a similar definition for the NS5s. Now, let's focus on the 3-dimensional theory, forget the coupling to 4-dimensional super young Mills. Then Gaiotto and Witten made a very simple conjecture that these theories flow to non-trivial strong coupling fixed points whenever this condition is valid for each gauge group, namely there are more than 2 number of colors hypermultiplets in the fundamental representation. This is a condition for complete Higgsing in the Higgs branch of the gauge symmetry. Now you can translate these conditions essentially with a little work to the conditions that the linking numbers of the 5 branes are ordered when you label the NS5 branes from right to left and the D5s from left to right. And actually by then moving, doing Hanani-Witten moves, moving all the D5s to the right and all the NS5s to the left, you end up with a setup like this where the linking numbers can just be read off as the number of D3 branes ending on any particular 5 brane. So you see that these guys define 2 partitions, rho and rho hat of some number n. And supersymmetry implies a partial ordering condition, namely that the Young tableaus associated to this partition satisfy this famous inequality, rho transpose bigger than rho hat, where the inequality of Young tableaus means that if you count the number of boxes in the first line, you have more on the left than the right, the number of boxes in the first 2 lines the same, and so on for all number of lines. Okay. Now, to summarize, therefore, Gaiotto-Witten conjectured that there are non-trivial n equal 4 superconformal theories. They label them T rho rho hat for any partitions rho and rho hat subject to this constraint, and they conjectured that this theory should exist. Let's go to the UCLA solution. So the UCLA group found this very general and very beautiful local form of solutions of the Killing spinor equations. And what's very nice about them is that they are described by 2 harmonic functions, H1 and H2, on a Riemann surface. So the form of the solutions is an ADS4 cross 2 sphere fibration over the Riemann surface sigma. And this is therefore the symmetries, the Killing isometries that we need for the background. And then if you give the 2 harmonic functions, you have the full solution. Here is the metric, for instance. Some complicated combinations of the harmonic functions determine the scale factors of the spheres, the ADS4 and the Riemann surface sigma. And there is a dilaton, which I wrote here. And there are p-form backgrounds, 5, 3, and 3-form backgrounds, which are again expressed this time not only in terms of the harmonic functions, but also in terms of the dual harmonic functions, namely holomorphic plus antiholomorphic as opposed to holomorphic minus antiholomorphic for H1 and the other way for H2. Okay, notice that there are some constant parts of these holomorphic functions which are pure gauge because they don't enter in H1 and H2 and they don't therefore affect the metric and the non-gauge fields. Okay, and with this you can write down some expressions. I won't stare at them a lot. But here is now, so this is the local solution, and the question is, what are the globally non-singular consistent solutions? Now, here is what happens. So the surface sigma can have boundaries which are interior points of the 10-dimensional geometry. So sigma can have a boundary, but 1, 2 spheres should shrink to 0 here, so that these points are actually normal interior points in 10 dimensions. According to which 2 spheres shrinks to 0, I denoted this by a red or a blue boundary. And there are three types of asymptotic regions or singularities on the boundary, which are basically corresponding to D5s, NS5s, or ADS5 cross S5 asymptotic regions. And the ADS5 cross S5 is the one that changes the boundary condition. The other ones don't. Here is, for instance, the local form of the NS5 singularity. You see, I have written down here the local form in a local coordinate where W equals to 0 is the position of the singularity. There is a logarithmic cut which is proportional to the number of NS5 branes, and the other harmonic function is constant, takes a constant value, and this constant value is related to the D3 brane charge, page charge, hidden in the singularity, so it is related to the linking numbers of the 5 branes in a given gauge. Here is the local form of the ADS5 cross S5 solution. It is a square root singularity now, like this, and the D3 brane charge is given in terms of these 4 coefficients, like that. And the stupid stumbling point, but which we ended up by realizing, and at the same time Maharoni and collaborators did the same, is that you can just take the H to 0 here. This caps off smoothly the asymptotic D3 regions, so you go smoothly from a domain wall to a conformal field theory, and the geometry is locally smooth even though the coordinates are singular. Okay, now here is the solution, the general solution after you put all these ingredients together. Here is a very explicit solution that should correspond to the linear quiver theories I showed to you. Okay, now you can compute in terms of these parameters of the harmonic function, the 5 brane charges and the linking numbers. I won't show to you this in much more detail. And as I said, you may have 0, 1, or 2 asymptotic ADS5 regions, but not more. This was missed in the original UCLA papers. More than 2 asymptotic regions seem to produce conical singularities in the middle, which we see no way for the moment to interpret. This means that these conformal field theories can be coupled to super Young-Mills on one side, the other side, but not on more than 2 semi-infinite 4-dimensional super Young-Mills theories. Okay, you can make various checks. In particular, the global symmetries of the CFT3 are realized as gauge symmetries on the 5 branes. And more specifically, we can show that the Gaiotto-Witten inequality is automatically satisfied in the supergravity side. And in a sense, this proves that we have a one-to-one correspondence between the solutions and what Gaiotto-Witten conjectured to be the strongly coupled superconformal field theories. You can actually also do something else. You can convert the linear quivers to circular quivers. I will not have time to explain details of this, but circular quiver theories can be described in a similar way, except now we cannot couple them to 4-dimensional super Young-Mills anymore without creating a singularity, or at least we haven't found a way to do it. Okay. Now, I will comment on this in a moment. There are several calculations concerning this rich set of holographic dualities that I don't have time to discuss. Let me just mention maybe 1 or 2. You can do free energy calculations on subgram CFT side. And for instance, for this very particular theory and related theories, Sassel, Estes, and Yamazaki computed exactly a 1/2 n square log n from supergravity that fits the gauge theory calculation. You can take K large and T-dualized to ABJM-like theories, and this we are studying still now, and I will skip the third point. In the last few minutes, let me go back to the original question. Now, we want to create a hierarchy of scales, remember? We want the radius of ADS4 to be much bigger than the radius of ADS5. This can only happen by taking degeneration limits of the geometry. So what are the degeneration limits? You can factorize 5 brane singularities, you can pinch the annulus, or you can cap off asymptotic ADS5 cross S5 regions. All these limits are interesting for different reasons. These things are warm branes of string theory. I won't discuss them here much, but let me go to the third one, which was what got us started. So we are basically taking the limit where the ADS5 crosses 5 throats are arbitrarily curved, which corresponds to taking the rank of the bulk super young Mills arbitrarily small, and that's what you get. Well, you do get something like Randall-Karch, but with one unfortunate problem, namely the ADS4 is now almost flat, but so is the compact 6-dimensional space-time that goes with it. So even though the graviton, the spin 2 mode, obtains a tiny mass, gravity is never 4-dimensional. Now this you can also see by looking at the warp factors, and this basically tells you what we need. It's very common, we have seen it in many places in string theory, in classical string theory, that hierarchies decompactify 10 dimensions, and that's one of the hard problems. But at least we know what we need. You see, here are the two criteria we need to implement the model that I showed to you in the beginning. First of all, we need a conformal field theory 3-pair, ADS4 pair, for which the compact space stays small. This means that you only have mu, a few other operators, and a large gap. That's a well-known, interesting, and hard problem, and I don't know if there are any solutions to this one. But you are not done. If you do find such a compactification, you have to make sure that you can couple this conformal field theory to super young Mills 4 without destabilizing the fixed point. And the fact that we found these conical singularities is ringing a bell that this may not be as easy as one may think. Usually one would think that you take any quiver theory, you just couple by fundamentals to any gauge group, and then you let them go to the 4-dimensional young Mills, and that's it. But the thing will flow under RG, and we don't know if this won't destabilize the fixed point. So we need to better understand these geometric singularities, and we are trying to do this now. And let me now summarize. Well, we found a large class of type 2b backgrounds that are duals of the Gaiotto-Witten theories and circular quiver generalizations. They have the nice feature that they have localized 5 branes and a lot of parameters, degrees of freedom, so that you can take degeneration limits and study them in great detail. The degeneration limits do correspond to couplings via small rank gauge groups. We failed to localize for the gravity because the brane fattens to the space-time. But however, this tells you the way in which this very thin throat should appear, and this is to be opposed to other efforts to create mass for spin 2 particles, like the papers of Kiritsis, Niarchos, Aharoni, Clark, and Karch, where they were trying to couple conformal field theories with local multi-trace deformations. Here, all you do is you just couple them with a very small rank group, and this is a throat, a wormhole throat, or if you cut it off, an asymptotic region. Last transparency, we all stared at this for the whole week, so here's the translation in case you were wondering what it says. Thank you very much.
So we finally know what things means there. We've been wondering during the entire conference. And is that true that second word is not even Greek, or not quite Greek?
Well, you see, it's not Attic Greek. That's why the second word, which is Ilios, sun, even the Greeks weren't understanding in the beginning. I had to Google it.
Okay. Okay, questions?
So, Kostas, you probably remember that when the mass of the or effective width of the graviton is larger than the curvature, then there is a new scale appearing, this strong coupling scale of the helicity 0. So what happens in this case?
So I'm never in this regime, obviously. So there is no Van Damme-Zakharov-Veltman discontinuity, because this mass I showed to you is always less. I mean, the range is always bigger than the radius.
So there is some kind of a...
So when you tune the brain to become flat, this thing goes to 0 faster, of course. So indeed, I avoid this.
So you are never in that regime. So this new scale is never appearing, basically, you are saying?
I don't think so, although,
okay.
yeah. I mean.
Any other question? Oh, Gaiotto then, yeah.
How complicated can the topology of sigma be, you think?
So the question is, what are the allowed topologies of sigma?
Right, so you had a disk and an annulus.
Yeah,
Do you think anything else
you know, we don't have a theorem of any sort. Of course, we try to construct your star theory, and this is singular also. But it may be we are being stupid. I mean, right now, all I know is that the non-singular solutions we can see are the infinite strip, the disk basically, and the annulus. But in the case of the annulus, there are no asymptotic ADS5 regions. There might be more solutions. It's an interesting question, but we don't find them.